Good afternoon, all of you. Today, my lecture on vapor compression refrigeration system. Myself, Krishna Kumar Karothiya, Assistant Professor, Department of Mechanical Engineering, IIMT College, Greater Noida. The content, 1 minute. Okay. So I will be talking in these few content in this lecture. First is the refrigeration. What is the refrigeration? Second, I will talk about the refrigeration effect. Third will be the unit of refrigeration, and fourth will be the it's a vapor compression refrigeration system. It's a, PS diagram and TS diagram. Then we will talk about the COP of vapor compression refrigeration and how we can calculate the COP for VCRS. Six, we will define the volumetric efficiency for the refrigeration system or reciprocating compressor. Then we will talk little bit about the different type of BCRS. Then we will talk about the subcooling in BCRS, and one or two numerical I will be giving the example on the BCRS numericals. So, course outcome of this lecture will be that at the end of this lecture, who are listening this lecture will able to learn the basic principle of vapor compression refrigeration system and different type of vapor compression refrigeration system and the COP of BCRS. So first, if we talk about the what is the refrigeration, so we talk refrigeration is the cooling basically. If we talk about, but in definition, it may define as a process of achieving and maintaining temperature below the surrounding temperature. Like here in this sketch, I am trying to explain the suppose surrounding temperature is 45 degree and we are able to maintain the 10 degree, so that is called basically refrigeration. If we second, if we talk about the refrigeration effect, so when we maintain the lower temperature, what we have to do, we need to extract some amount of heat from that space, and that amount of heat actually we call the refrigeration effect in term of heat, or in represent we kilojoule basically. So definition, it is the amount of heat which is to be extracted from the storage place in order to maintain the lower temperature. So here you can see the 45 degree centigrade is surrounding temperature, 10 degree in the space where we are maintaining a refrigeration effect or cooling. And in order to maintain this 10 degree centigrade temperature, we need to remove some amount of heat from that space. So that amount of heat basically we call the refrigeration effect. Then one the famous term in the refrigeration or air conditioning, generally we talk the unit of refrigeration or tons of refrigeration. So if we go to the market and we purchase the AC, so generally we talk 1 TR AC we want to purchase or 1.5 TR of air conditioning we want to purchase. So what is actually that? So if we define that, it is defined as the amount of heat rate which is to be extracted from 1 tons of water at 0 degree centigrade in order to convert 1 tons of ice at 0 degree centigrade in 24 hours. So if we suppose this is the one space, and here we have 1 tons of ice, or you can say the water. Okay, if we want to convert that water into ice in a specific time, that is called 24 hour, and the tons is US ton basically we talk here, and in the kg it is around 907 kg. So that amount of heat we extract from the water in order to convert that water into ice in 24 hours. So that amount of heat generally the 1 TR or 1 tons of refrigeration, or you can say unit of refrigeration. If we calculate in numerical term, TR equal to 907 the mass of the water multiply the latent heat of the water divide by the time 24 hour into, if we want to convert in the minutes, we multiply second, multiply 60 if we want to convert in the second. Okay, so this first for the minutes, this second 60 for the second. So this come around 3.5 kilojoule per second, and that is the kilowatt. So 1 TR equal to 3.5 kilowatt. So if we purchase 1 ton of air conditioning, generally its rating is 3.5 kilowatt. That amount of heat it is capable to remove from the storage place or from the room actually. Okay. Then we talk in the commercial fridge or air conditioning. In our house, there are fridge, air conditioning. So these all the most of the component of or system of the refrigeration air conditioning work on the vapor compression refrigeration system. So we will talk about the vapor compression refrigeration system. So here you can see the household fridge is there. Okay. So there are mainly four components in that. First is you can talk about the compressor, then condenser, then expansion, then evaporator. If you try to locate in our fridge that upper part where we have the ice cube cabinet, the it is called the evaporator, and backside the coils is there where we call the condenser, and the bottom we have the black boxes, it is basically compressor. And where we place our vegetables and waters in the fridge, basically this is called the evaporator, or inside that there is a evaporator call. Okay. And in between that condenser and evaporator we have the expansion device. Okay. In that the refrigerant produce the cooling, or you can say reduce the temperature, which goes to evaporator where it affect the refrigeration effect in the fridge cabinet. So how it is happening, we will see in next. Similar fashion, our air conditioning also work on the window air condition, work on the vapor compression refrigeration system. Here also the similar concept is applied in the modify structures. Okay. So in air conditioning or in fridge, what is the major difference is that the refrigeration we need to maintain very low temperature like 0 degree centigrade or -5 even, or 5 degree. But in air conditioning we are maintaining the temperature for the human comfort, because air conditioning designed for the human being. Okay, generally we use. So the comfort temperature for the human being is around 25 degree centigrade, and relative humidity around 55 to 60%. Okay. So that is the point where we want to achieve from the air conditioning, okay, for the human being. So here this air conditioning also work on the vapor compression refrigeration system. Like here, our room or this front coil will work as a evaporator, and backside coil will work as a condenser coil. And this one black box, you have the compressor, and in between there are condenser, or in between condenser and evaporator, you have the expansion coil, okay, or expansion device. And additional component here, the condenser fan and blower, which is provide the flow of the air to inside the room and from the uh, room also. Now you can talk about the vapor compression refrigeration system. So the cycle is based on the four component as I have talked about earlier. Like compressor, it have got the condenser, it have got the expansion valve, and it has got the evaporator, which is assembled in series and produce the refrigeration effect. So generally, if we talk the vapor compression refrigeration system, we need to explain on the pH diagram or either TS diagram. So for the pH diagram of the this BCRS, we have P on the y-axis, we have H or enthalpy for the x-axis, P for pressure. Okay, and we make the pH diagram like this. And here the first point after the end of the evaporation and starting the compression, then it goes to the condenser, and after that it goes to the expansion or expansion device, then where the cooling is produced, and after that it goes to evaporator where the refrigeration or cooling effect will be given to the substance or things. Okay. So here also I have make the temperatures here, like condenser if you have 35 degree centigrade, and after expansion it got the 5 degree centigrade in evaporator, and in evaporator it absorbs the heat from the storage place, and that refrigerant actually the in piping system, what is that, the refrigerant of refrigeration. So basically R134A is there. Okay. So basically that temperature of refrigerant is reducing and increasing, and according to that our the space is getting cooled. Okay. So here you can see the 5 degree centigrade the temperature of the that refrigerant. Okay, when it come in contact with the water or vegetables in our fridge, then it absorb heat from surrounding, because the heat will flow from the higher temperature to lower temperature. So here if you have the high temperature substance, then its heat goes to the lower temperature. Okay, and the temperature of that substance will decrease, and when that heat coming to the refrigerant, its temperature gets increased, and that refrigerant are very sensitive. If the temperature is increased, they convert in the vapor form. So after the converting in vapor form, while absorbing the heat from the surrounding, it goes to the compressor, because compressor accept only the vapor uh, refrigerant. It cannot compress the liquid refrigerant. So refrigerant has to be converted in the vapor to go into the compressor. Then only it will be compressed. Okay. So after the compress, it need to be cool down. So how we can cool down? With the help of the condenser. In our fridge, generally there air cooled condenser are there where its temperature decrease. Okay, and also the phase of the refrigerant. Like in compressor, we have vapor form. In condenser, it convert the from the vapor to the liquid. Okay, and after that is go to the expansion device or capillary tube, you can say, where its temperature and pressure will go decrease, and again it go to the evaporator where it absorbs the heat from the surrounding, and then itself it goes become vapor, and again it go to the compressor. So here you can see in the pH diagram, this area basically is superheated. This is the wet region. This is the liquid region. So if we compress from this vapor region, it got superheated in the compressor. Then if it goes to the condenser, the phase of the refrigerant will change, and the latent heat of refrigerant also release. Okay, then after that it expands, so where you can see the pressure is decreasing at the downside. Okay, and as well as if pressure is decreasing, the temperature also decrease. So we are able to produce the cooling effect or lower temperature, and that lower temperature refrigerant we supply in the evaporator coils or piping system. And surrounding piping system, we have the substance, or you can say the vegetable in the fridge, if you talk about, or if we talk about the uh, air conditioning, there will be the blower air. Okay, so the fan air will flow over the that evaporator, and that air come in contact with the evaporator, then it goes cooled, and it that will circulate inside the room. So that is how the basic working model or working principle of BCRS refrigeration cycle or system. Here also the schematic diagram of that PS diagram you can have. Like here 1 to 2 you will have the compressor, then 2 to 3 you will have the condenser, and 3 to 4 you have the expansion valve, and 4 to 1 it is the evaporator. Okay, so same thing is happening here, but this is the schematic diagram. Like here 1 to 2, the pressure and temperature increasing of the refrigerant in that pipe, uh, in the pipe. Okay, if then it goes in the condenser where the phase of that refrigerant will change, as well as the latent heat of refrigerant released to the atmosphere, then only the phase will change. Okay, after that it expand in the expansion device. Okay, between 3 to 4, and 4 to 1 is it absorbs heat in the evaporator. Okay, then again it goes to the compressor. Then if we talk about the vapor compression refrigeration system over the TS diagram. Okay, so PS diagram we have already discussed, I think. Similar pattern you can explain or you can have on TS diagram, because when we are talking about the cooling, the temperature also that should represent. Actually here we can represent the pressure. But on TS diagram, we can represent the temperature also. So here, uh, similar fashion here, 1 to 2, this process is a compression. Okay, isentropic compression generally is called. Then 2 to 3 is called the constant pressure heat rejection in the condenser. Okay, then process 3 to 4, it's called the throttling process in the expansion device or in the capillary. 4 to 1, it is called the constant pressure heat absorption in the evaporator. So basically these are the four processes which are involved in the our fridge or air conditioning, or you can say in the vapor compression refrigeration system. So first you can say isentropic compression is taking place 1 to 2. 2 to 3, the constant pressure heat rejection means the pressure is not changing, but the heat is rejecting. Which heat? The latent heat. So that the refrigerant phase from vapor to liquid can be possible. And 3 to 4, it is basically throttling process in the expansion where the pressure and temperature is decreased. And after decreasing that pressure, temperature go to evaporator. So this is the representations of BCRS over the TS diagram and pH diagram. Now we will talk about the COP of vapor compression, how we can design the refrigeration system so we can save the energy in order to produce the refrigeration effect or in cooling effect in the air conditioning system. So as a design engineer, we should think about how we can save the energy in order to create the refrigeration effect. So first we should know the what is the COP. COP is the coefficient performance of vapor compression. Basically, if we talk about it, is the definition of COP generally the refrigeration effect divided by the work input. Okay, so the steady flow energy equation we can apply for the vapor compression system like here. Okay, for compressor also we can apply that steady flow energy equation. For condenser, for expansion, or in throttling process, generally what properties of throttling process have, the enthalpy remain constant. Okay, and evaporator also we will apply an steady flow energy equation, and we will determine the refrigeration effect and work input, and we divide the refrigeration effect, uh, or you can say refrigeration effect divided by the work input. So here you can have, so in compressor you can see here, compressor is fitted in 1 to 2 process. So at the initial level of compressor you have the enthalpy. Okay, so you can have enthalpy H1. Okay, then plus we are giving some work in the compressor. Okay, so you can have like this here. So this is the PS diagram. You can have 1, 2, or this. Okay, so 1, 2, 3, and 4. Direction is anti-clockwise. Okay, like this. So we can make here. So here we are talking about the compressor. So this compressor is fitted between the 1 to 2 process. So here at the initial step or the inlet of the compressor, we have the energy at H1. When we are giving some work input in the compressor, it compress the refrigerant basically. So we need to add the WC is the compressor work. Then it reaches to the point 2 where we can define the at that level of energy. That is we represent with the help of the enthalpy. This is the P, and this axis we have H, pH diagram. Okay. So here also the H2 you can represent here. Okay, so this is the steady flow energy equation for the compressor. Okay, Q plus Q, but in isentropic process we assume that the process is isentropic, so in that the Q or the heat transfer will be negligible. Okay, so we reduce the Q to the 0, and which become W equal to H2 minus H1. So that is the compressor work we are giving in the VCRS. Then second component we have the condenser. Then condenser inlet energy we have H2. Then the some amount of heat rejection is taking place from that condenser. So that is QR, the heat rejection equal to H3, because this is the final destination of that condenser. Okay, so that level of energy at point 3 we represent with the help of the S3 plus the W if we are giving or taking some work from the condenser. But in condenser we are not giving any work, or is neither we taking any work from the condenser. So the W become 0 or negligible. Then heat rejected will be the H3 minus H2, and that should be in the negative because the heat rejection is taking from the system. So the heat rejection sign of for the rejection is always represent in the thermodynamics with the negative sign. Okay, so generally we represent H2 minus H3 in the negative form, but while calculation we don't represent that minus, because we assume that whenever the heat is rejected from the condenser or from the system, it always is negative. Okay, so that is the equation for the condenser. Then throttling, we already know from the thermodynamics that enthalpy remain constant in the throttling process. So at the inlet you have the energy level H3, at outlet you have the energy or enthalpy at the 4. So that enthalpy remain constant. So this line should be state or constant enthalpy line. Then we have fourth component like evaporator. So steady flow energy for the evaporator like inlet or outlet, what we have point. Inlet you have the point 4, so enthalpy at the point 4 plus in evaporator what we are doing, it absorbing the heat from the storage place. Okay, so we add the QA absorption of heat equal to what is going to output the H1 point. So we represent with the help of the H1 and plus W if we are taking or giving some work. But in evaporator also we don't giving any work or neither we taking any work from the evaporator. So W become negligible or 0. So the equation become for the evaporator QA equal to H1 minus H4, which is also we talk the refrigeration effect. Okay, so this is our work input in compressor, and evaporator we are getting the refrigeration effect or our result what we want. So if we talk about the COP of the system, that is basically refrigeration effect divided by the work input. So refrigeration effect, what is the amount of heat which is absorbed from the storage place, and that uh, heat is absorbed is QA. Okay, which is in term of enthalpy H1 minus H4. So this H1 is here and this H4 is here. Okay, so in term of enthalpy, we want to define the COP, that H1 minus H4 divided by H2 minus H1. Okay, and here you can see the enthalpy at the point 3 and 4 equal. So this equation we can write, or in place of H4 you can have the H3. So COP equal to H1 minus H4 divided by H2 minus H1 equal to H1 minus H3 divided by H2 minus H1. Okay. So this is we have saw the COP equation for the vapor compression. Then we also need to define the power input to the compressor actually. Okay, so how we can define the power input to the compressor? 1 minute, can I remove this? I can remove this thing. 1 minute, hold on. So the power input to the compressor, how we can define. So the equation for the power input equal to m the mass flow rate of refrigerant multiply the work input in the compressor. So we already know the work input in the compressor. We have in previous slide we have defined with the help of the H2 minus H1. So the power input in the compressor we can have mass flow rate of refrigerant multiply the work input in the compressor. So this become m dot multiply or in bracket H2 minus H1 bracket close in kilojoule per second or in kilowatt. Then uh, that power, or you can say in BCRS, we also need to define the refrigeration capacity. So mass flow of refrigerant multiply refrigeration effect. So refrigeration is taking at the uh, process of 4 to 1 where the evaporator is fitted. So the equation for the refrigeration effect is H1 minus H4. If we multiply with the mass flow rate of refrigerant, is become the refrigeration capacity in kilojoule per second. So that two term also used for the designing of BCRS or refrigeration system. Okay, so keep remember these power input to the compression and refrigeration capacity. Then volumetric efficiency of reciprocating compressor. So a reciprocating compressor, as we know, the linear movements, okay, it compress the gases, but here the refrigerant as a gas is for the compressor. Okay, so if we define the volumetric efficiency of reciprocating compressor, it is the breathing capacity of compressor, and it is defined as the actual volume of refrigerant entering in the compressor to the swapped volume. Okay, so we need to define here the actual volume and swapped volume. Okay, and we multiply these two terms, then we got the volumetric efficiency of the reciprocating compressor. So if we assume that m dot is the actual mass flow rate of refrigerant and small v is the specific volume of refrigerant at inlet, then actual volume flow rate will be, and this volumetric efficiency term what we are talking, we define and we explain at the inlet of the compressor only. Okay, so actual volume equal to m dot multiply specific volume and swapped volume pi by 4 d square l. And if the speed of the compressor is there, we also can multiply the n here. Okay, yeah, and where d is the bore diameter or cylinder diameter of the reciprocating compressor, l is the stroke length, and n is the speed of the compressor. If the one cycle is completed in n revolution per minute, then we have the soft volume pi by 4 d square l multiply n, and hence volumetric efficiency we can have the eta equal to the actual volume flow rate divided by the soft volume. Okay, so you can say that volumetric efficiency, if you compare with our heart system, so like our heart system have capacity of 3 liter of inhaling of oxygen, you can say, but it is inhaling at around 2 liter. So how we can 2 divide by 3, we can define the if volumetric efficiency of our heart. Okay, similarly here also, if the cylinder capacity is the like 100 meter cube and it is only able to the flow 80 or 80 meter cube, so the 80 divided by 100, it become the volumetric efficiency of that system. Okay, so that is how we can define. Okay, 1 minute. So that is how the volumetric we can define, and it is used in the BCRS system to determine the size of the cylinder. Okay, or reciprocating compressor basically. Okay. Then if we talk about type of BCRS system, it is called in 3 types: simple BCRS system, wet BCRS system, or superheated BCRS system. Okay, so if we talk about simple system, that starting of compressor point always start at the saturated line, and here you can see, if we 1 minute here. Okay, so this is the saturated, and here this 1 point at the wet region, and this here 1 point at the superheated. So based on this point, 1 point, we define the BCRS system. If it is start from the saturated vapor point, then it is called the simple BCRS system. If the compression is starting from the wet positions, like here you have the dryness fraction and wet region, then the system is called the wet vapor compression. If it is starting from superheated region, then the system is called the superheated region. And while the explaining the numerical, you will see the difference if the compression is taking from this point or from this point. Okay, so this is the 3 type of VRS system. Okay, then subcooling is taking place in the with the help of the if we apply another heat exchanger. So with that help of heat exchanger, you can create actually subcooling. For subcooling, you need to decrease the temperature at the outlet of the condenser from 3 to 3 days, and if we are decreasing that temperature, then it somehow it is adding that temperature. So at the inlet of the compressor, it is adding that temperature or increasing that temperature. So, here the superheating is taking place, here the subcooling is taking place. Okay, so this is the basic equation for the subcooling in PCRS. We know that heat loss equal to heat gain. We assume that perfectly here, that whatever heat is decreasing at the outlet of the condenser, it is gaining the inlet of the compressor. So this is the equation for the subcooling: S3 minus S3 dash equal to S3 dash equal to H1. And for this, the specific heat of the liquid here will be multiply, and the enthalpy we know that in term of temperature we can put T3 minus T3 dash equal to Cp of vapor refrigerant multiply T1 minus T1 dash minus T1. So that is how the equation for the subcooling in BCRS is. Okay, so thanks for watching this video. I hope you people like this, and thank you very much. Have a great day.